Welcome back to the channel. In the previous video, we explored tree of thought at a prompt level that gave us an intuition of what tree of thought is. Today, we are going to focus on why tree of thought was needed in the first place. To understand that, we need a problem that is simple to describe, easy to verify, and brutally unforgiving to bad reasoning. That problem is the game of 24. So in this video, we are going to do two things. First, we will walk through how the tree of thought paper uses game of 24 example to expose the limitation of chain of thought reasoning. Then we will implement a true tree of thought solver in Python where you can actually watch branching, evaluation, pruning, and search happen step by step. The game of 24 gives you 4 numbers. You are allowed to use addition, subtraction, multiplication, and division exactly once per number, and your goal is to reach the value 24. On paper, this looks trivial, but in practice, it's a perfect stress test for reasoning systems because almost every early decision matters. If you choose the wrong operation early, you don't just get a wrong number, you eliminate the possibility of any correct answer downstream. That's why the authors of the research paper we saw in previous video chose the game of 24 as their primary example. Not because it's a math puzzle, but because it forces reasoning to behave like search, not narration. Instead of asking the model to explain its reasoning, paper asks a different question. What if we let the model explore multiple reasoning paths, evaluate partial solutions, discard dead ends, and continue only the most promising ideas, the way humans actually solve puzzles? That shift from linear explanation to a deliberate search is the core idea behind tree of thought. So let's dive in. So what is game of 24? Game of 24 is a classic mathematical reasoning task. You are given 4 numbers. In this case, I'll scroll to the section. Where is game of? Yep, game of 24. So we are given 4 numbers, which are 4, 9, 10 and 13. Your goal is to reach 24 by combining all 4 numbers exactly once using only the operators addition, subtraction, multiplication, and division. So a solution could look like 10 minus 4 multiplied by 13 minus 9 equal to 24. So this problem is what game of 24 is all about. When the researchers evaluated the game of 24, they first tested standard chain of thought prompting. Even with GPT-4, when explicitly asking the model to reason step by step, performance was extremely low. So you can see that the GPT-4 solved only about 4% of the game of 24 problems using chain of thought. And that result is important because it shows the limitation isn't model size or math ability. The limitation is a reasoning strategy. Chain of thought follows a single linear path, and in a problem like game of 24, one wrong early decision completely kills the solution. The researchers then applied this problem to tree of thought framework. With the tree of thought framework, where the model explores multiple intermediate states, the success rates jumped to around 74%, and they have linked the code repository in case you want to take a look. This is not a small improvement. It's nearly a 20-fold increase in the accuracy, achieved not by training a new model, but just by changing how the model reasons. The results make one thing very clear, that for problems that require look ahead, backtracking, and strategic exploration, reasoning as a search process is fundamentally more powerful than reasoning as a single narrated chain. Okay, so let's implement game of 24 using a Python example, and we understand how the theory becomes an actual algorithm. So we start by importing some of the libraries that we need. I'm using Grok with Llama 3 again. Here I am configuring Grok API key, and there is a clear message. If it is missing, then I'm setting up Grok client and then model. So there is a helper function here, which is making calls to chat completion APIs. It's just taking a system prompt and user prompt, which is a normal, simplest helper function. Basically, the critical thing is that the model is not solving the puzzle. Python handles arithmetic perfectly. The LLM's role here is exactly what tree of thought paper describes. It acts as a heuristic evaluator, deciding which partial solutions are worth exploring. Okay, so next one is a class, which is the name is state. This is the most important structure in the entire file. In tree of thought paper, a thought is not text, it's a state. This state represent remaining numbers. In this case, how those numbers were produced, like the expressions using which those numbers were produced, the sequence of operations, the steps taken to produce those expressions and operations, how deep we are in the tree, and how promising that path looks using the score. This is thought decomposition made explicit. Next come a system prompt, which is always going to be the same. It says that you are an expert puzzle solver. You are scoring partial game of 24. States how promising they are. Return only a number from 1 to 10. The next function is solved. This function simply checks whether we have reached the final state, which in this case is 24. The next function is expand, which implements branching. For every pair of numbers, we apply addition, subtraction, multiplication, and division. Each operation creates a new child state, and we are appending each child state to this array here, this list. And this is where the tree grows and where most paths will eventually die. Next comes a score state. This is where the LLM enters the loop. So we are asking the model with each partial state that how promising is the state for eventually reaching 24. And the model returns a score from 1 to 10. Next is taught beam game 24 function. Now we arrive at the core algorithm. This function implements tree of thought using beam search, which the paper shows in both effective and efficient. So the initial state here is we begin with the single root state, the starting numbers. This is the root of the reasoning tree. And then we start the beam with just one node, that is the initial state. Next one is the loop itself, the multi-step search. So the loop is search running over time. So we are putting range 3 because with 4 numbers we need exactly 3 merges to end up with one number. So next is the candidate list. At each depth, we build a list of candidate states. This is like the next frontier in the search tree. So we just initializing the candidate. Then we take every surviving state in the current beam and call expand function on that, which is branching step. So we branch out the surviving solution. Then expand is generating all legal next moves. Pick 2 numbers, apply those 4 operators, and create new states. That's the tree part of tree of thought. Each child is a branch. Then we check did the branch already reach 24 using isSolved function. If yes, we stop immediately and return the solution and assign a score. So the moment any branch reaches the target, we don't waste any compute exploring other branches. And if it's not solved, we score the child state using score state function that we saw above. This is the state evaluation, one of the core ideas of taught paper. Is the partial state promising or is it a dead end? And the score becomes heuristic that guides the search. Now comes the most important part here. We sort all the candidates by score and keep only the beam width state. This is beam search. Conceptually, we explored many branches. Then we aggressively cut the tree down and we continue only with the best branches. That's how taught stays powerful without becoming exponentially expensive. Then verbose. Basically, when verbose is on, we print top states after each depth. This is perfect for video because you can literally watch which branch survived, which numbers remain, and which operations got us here. So once we run this function, you would see in detail. So next comes is this part. After 3 deep depth levels, we check if any surviving beam states actually solve the puzzle using isSolved function. If yes, we return the best one we found. If not, we return none. Meaning the current beam width and pruning settings, we did not find a solution in this run. Now look at the main function. We are passing those 4 numbers from the paper, which are 4, 9, 10, and 13. And then we run it through this function, which we just saw, and we see the result. Let's run this function and see what it returns. Okay, let's look at the output now. Each section of the output corresponds to one depth in the reasoning tree. So depth 1 here means we have made exactly one arithmetic combination. Depth 2 means we have made 2 combinations. So because we start with 4 numbers, we will only need 3 depth to reach a final answer. The top 5, let's look at depth 1. The algorithm explores many possible first moves, but only top 5 survive. What's important here is the kind of number that are being preferred, which are very, very small. Instead of chasing large number like 10 plus 14 is 24, it's deliberately favoring small structured numbers like 1, 3, 4, 6, because these numbers act as building blocks. It's the first depth. There's already a major difference from native chain of thought, because Cort would commit to one move, which will be a bigger number like 13 plus 10, which makes 23, and that never recovers. So this always start with a small number so that it can easily backtrack and choose a different path. The next we talk about depth 2. Now this is a critical moment. At depth 2, one state stands out immediately, which is 4 plus 4 multiplied by 6 is already 24, and the algorithm has given it score 10. This is not luck, it's evaluator doing exactly what tree of thought paper describes. The moment the search reaches 4 and 6, the problem is essentially solved. These are, notice something subtle but important. We never even print depth 3. That's because the algorithm terminates early. As soon as a guaranteed solution is detected, there is no reason to expand the tree further. That's exactly how Torch saves compute. It searches just enough, not more. So that's our final answer. Notice how the solution is given in steps, not as one big explanation, but as a sequence of selected decisions. That's all I wanted to cover in this video. If this helped you understand tree of thought at a deeper level, please like the video and subscribe to the channel. It really helps for watching, and I'll see you in the next deep dive.